Welcome everybody to the Spoken Nerd, the podcast about database technology. I'm your host Connor McDonald, and in this session, well, I'm a bit torn. I've just got back from the DOAG conference, and a few people came up and said hello, which was fantastic, and a few more people spoke about the podcast. The first person that came up and said, "Oh, yeah, Connor, I'm listening to the podcast, and I especially like the ones where you just talk by yourself about basics and fundamentals. I'm not so much of a fan of the ones where you have guests." And I took that on board. And then the very next person that came up and said, "Yeah, hey, Connor, I'm listening to your podcast. I'm not sure I like the ones which are just by yourself because podcasts are meant to be with multiple people." So I find myself in a bit of a quandary here. And I suppose that's a reinforcement of the old adage, you can please some of the people some of the time, but you can't please all of the people all of the time. I suppose I'll just keep bouncing back and forth between having guests and not having guests as long as people are prepared to come along and chat with me about technology. In this session though, we're going back to basics and it's just me behind the microphone today. I'm going to talk about tables. Now, to be honest, I was thinking I would talk about the different types of tables and how they're structured and how they're all put together. But as I did a bit of research, I realized that that would be way too much to even think about covering in a single session. To give an example, how many different types of tables do you think there are in an Oracle database? Most people would think, oh yes, well I've got a heap table, I've got an index organized table. I'll come back to those in a second. But after a bit of thought, I realized there's actually 9 I could think of. Let's go through them. Number 1, a heap organized table. As the name suggests, data comes in, you just literally throw it in a heap. Rows get scattered throughout the table, hence the term heap table. Then we have indexed organized tables. These are tables that are structured or stored as an index, and because indexes always have some sort of order to them, the table has to have a primary key which defines the ordering of the data. Then we've got clustered tables. Most people probably don't regularly use clustered tables in day-to-day basis, but I would argue that every single person running Oracle is using clustered tables extensively, perhaps without their knowledge. That is because the data dictionary is predominantly made up of clustered tables. Clustered tables are where more than one table will have their rows stored together on the same physical block. And that makes a lot of sense in a data dictionary style of operation where, for example, we have a list of tables and the list of columns and so forth. It makes sense to store those things together. Then we have hash clustered tables, our 4th type of table. That's the same as a clustered table, but we use a hash function in order to distribute the data. Number 5, you've got nested tables. Nested tables came along in 8.0, I think, when object relational databases were all the rage and Oracle was looking to get some of that action. And so we ended up with the concept of nested tables. Along the 8.1 or 8i timeframe, we now had our 6th type, which is global temporary tables. Global because you define them once, that definition is stored in the dictionary, but each session gets its own private copy of the data, and that data is transient or temporary. As soon as you commit or when the session finishes, the data is lost forever. 18c extended that to have private temporary tables. Tables that are so fleeting, they don't really even exist in the data dictionary. They are stored in local session memory and therefore can have a totally flexible structure. You might be thinking I'm running out, but no, we've still got more. Around the 9i time frame, I think we have external tables, the ability to define a table, which in fact is really just a mapping of external data, typically in a flat file somewhere that you could now query from the Oracle database. More modern versions of the database have huge amounts of flexibility there. You can get the flat files from object storage, they can be Parquet, they can be big data, all sorts of mechanisms by which you can run SQL against some form of data which is not stored in the conventional relational format. And also we have object tables. Once again, a throwback to the object relational hype of the late 90s and early 2000s, tables that are defined as tables of object types as opposed to conventional rows and columns. So even there, I've burnt a fair few minutes just talking about the types of tables we have and not even diving into any kind of detail about them. It was a ridiculous amount to try cover in one session, and so I had to drag things back down to something a bit more manageable. Then my plan was to start with, well, let's do a session just on heap tables. And as I started thinking about the topic of heap tables, even that started thinking, well, that's going to be a 7-hour podcast episode which no one is going to listen to. So I had to drop it down even further, and I thought, let's just maybe think about the create table command. And even that when I went and looked at the documentation. If you've ever looked at the create table or alter table sections in the SQL language reference, you can literally be pressing page down for a good few minutes while you go through all the possible options. And so for this episode, I suppose I've really cut it down to just one simple thing. What happens when I have a table which is already created, it's a heap table, and I just insert one row? And that's all I'm going to talk about in this session. How does a table grow? So let me start with any simple heap table. I've simply done create table. It can have 1 column, 2 columns. It doesn't really matter. All we know is we run a create table command. The database has come back with, yes, your table is created, and that table is totally empty. Now, when I say totally empty, it's not just devoid of rows. It actually is devoid of any space consumption on the database as well. It literally consumes 0 space on the database. This didn't used to be the case. It used to be the case that whenever you created the table, we would immediately give you some sort of space allocation for that table. I can't remember exactly when, but we introduced a parameter some versions ago called deferred segment creation, which is defer the creation of a segment being something that physically occupies space in a data file, until we actually put some data into that table or that segment. I think the background for this enhancement came from Oracle E-Business Suite. When you install E-Business Suite, which is a massively complicated product, you're creating somewhere in the order, I think, 25 to 30,000 tables. Now, some people don't use all the components of E-Business Suite. You might have E-Business Suite, but just use, say, accounts payable, or you might just use accounts receivable, or maybe just the payroll section. My understanding is that to ease the complexity and maintenance regime of E-Business Suite, whatever components you use, we always install the whole bundle as a single unit. That means you might have, out of your 25 to 30,000 tables, maybe 20,000 of them might be empty. And obviously in times gone past where every single create table command would at least allocate some space in the data file, you would be burning up a lot of space on your database just for a whole stack of empty tables. Deferred segment creation came along such that when you create tables but never ever use them, they're just required to be part of the product, then we're not going to consume any space or waste any space on your database for that purpose. In either scenario, at some point, you're going to allocate that first extent for your table. It'll either be immediately as you create the table, if you have deferred segment creation equals false, or it'll be the moment you put that first row into a table. We're going to go out to the data file and grab a single extent, which is typically going to be 64K or 1 megabyte, depending on how your table spaces are created, and that is given to this table. That table now owns that chunk of disk space. For the rest of this discussion, I'll assume we've grabbed 64K, the first extent for that table. I've inserted my 1 row, I've committed that 1 row, and therefore my table now consumes a single 64K extent. If I do a query on that table, just select star from my table, you would imagine that we need to query at least 64K. We've allocated 64K to that table. I'm doing a query. Somewhere in there is that 1 row. I'll need to scan that 64 kilobytes. That is not what is required. And as you can imagine, that doesn't sound particularly efficient to scan 64K, even though there's only 1 row. Inside the table, we hold a marker which we call the high watermark. Now, please bear with me. What I'm going to explain now is somewhat of a simplification, so we can at least have a basic understanding of the high watermark. We're going to extend this shortly. So please don't go out flaming me on Twitter saying, no, that's wrong. Bear with me. We're going to keep adding more and more descriptions and understanding as we go on through this session. Let's assume a typical database block size of 8K. Most databases have an 8K block size nowadays because of the default. So my 64K extent will be 8 lots of 8 blocks. If I've just inserted 1 row, only one of those blocks is going to contain that 1 row. The database will record a thing called the high watermark for this table. I have 8 blocks, i.e. 64K, allocated to my table, but I've only used 1. So we will have a high watermark of 1 block. That's all I need to scan if I do a select star from my table. Let's now assume we added another, say, 100 rows into my table. And let's assume that due to the size of the rows, I've now occupied 4 of the 8 blocks that were allocated to that extent. For the sake of keeping things simple, let's assume those blocks are 1, 2, 3, and 4, and blocks 5, 6, 7, and 8 are yet to be used. Out in physical storage land, my table still occupies 64K, 8 blocks of disk space. There is data inside the table only in blocks 1, 2, 3, and 4. The high watermark for my table is now block number 4. A full table scan will not need to scan all 8 blocks. It will only scan blocks 1, 2, 3, and 4 because I know that the high watermark is block number 4. I want to stress, a full scan is not exactly the simply case of scanning the blocks inside the table. If you head to one of my previous podcast episodes where I talk about how does select star from table work, you'll see we talk about things like segment header blocks, extent map blocks, etc., etc. But once again, for the sake of simplicity, let's assume a full scan of those 4 blocks simply reads blocks 1, 2, 3, and 4. The second reason it's a simplification is we're dealing with a very small scale here, only a 64K extent. Yes, the database is going to simply go to the operating system and say, yep, I'd like to read blocks 1, 2, 3, and 4. The operating system itself might go, well, while I'm out here, I might read a megabyte from the storage and just hold that for you. So when I say a full scan just reading only 4 blocks, you need to take that with a grain of salt, but you get the idea of what we're trying to explain here. We use the term high watermark as perhaps a metaphor to things like floodwaters when we have things like storms. The high watermark always represents the maximum amount of space used in this table. Thus, DML can only make the high watermark go up. It can never go down. If you insert more rows, we'll consume more blocks, and therefore the high watermark will go up. If you delete rows, it doesn't matter if you even delete all of the rows, the high watermark doesn't change. Yes, we will clear out the space from those initial blocks, but the high watermark stays at 4. If you do an update, it might change the high watermark, but this is typically rare. The reason why an update might change the high watermark is you might take a row which is quite small in size and update it to a much larger length row. That might mean that the database needs to relocate that row to a brand new block. And therefore, if I've used up blocks 1, 2, 3, and 4, it's possible that that relocated row needs to go to a brand new block number 5, and then the high watermark would go 1, 2, 3, 4, 5. The high watermark is important when it comes to doing a full scan of a table, because as I said, we scan all the blocks from the start of the table up until the high watermark. In this simple case where I've got 4 blocks, 1, 2, 3, and 4 containing data, scanning the table will scan 4 blocks. If I delete all the rows from my table, the high watermark is still 4, even though the table is now logically empty. Therefore, a select star from my table to return no rows will still scan 4 blocks. If you scale it out to a more real-world situation, you might have a table with, say, 10 million rows in there. If you were to delete all of those rows, the high watermark will still be very, very high, the high watermark being the highest block that we required to store those 10 million rows. A full table scan of that table, now that you've deleted all of the rows, will still be quite slow because we start at the beginning of the table and we scan every block up until the high watermark. The question naturally becomes, how do we adjust or shift the high watermark should we want to? We've seen that DML, in particular insert, will push it upwards. Can we in any way bring it downwards? The only way of doing this is with DDL, data definition language. The easiest way to bring the high watermark down? Well, you could just drop the table. Then there's no high watermark because there's no table as well. Perhaps slightly less brutal is to truncate the table. When you truncate a table, you have logically erased each row from the table, but the way we implement it is simply to shift the high watermark from its current position down to block number 0. All the rows are actually still there, they're just no longer referenceable because the high watermark has shrunk all the way back down to the start of the table. Just by way of completeness, there are 2 options when you use the truncate table command that aren't related to the high watermark, but related to the physical storage of the table on disk. If you do truncate table drop storage, which is the default, not only do we reset the high watermark, but we release any extents that were allocated out on the operating system data files back to the database such that that space can be used for other tables. If you use truncate table reuse storage, then we still reset the high watermark back to block number 0, but all the various extents that were allocated to that table remain allocated to the table. Another way of adjusting the high watermark is using the alter table move command. This is equivalent to a reorganization of the data. We are logically unloading the data and reloading it into brand new blocks. This will alter the high watermark. Most probably, and this is the most common motivation for doing alter table move, this will result in a lower high watermark because we're often trying to reclaim deleted space. But there's no guarantee of this. If I take a table which only has ever had 1,000 rows inserted into it and do alter table move, I'll end up with a table with 1,000 rows in it again and probably an unchanged high watermark. Conversely, if I had a table where I have used up all the various percent free area inside each block, then an alter table move may indeed make the high watermark higher because we are now going to put back in that percent free setting that we normally have for every single block. Another way of adjusting the high watermark is with the alter table shrink space command. Similarly to truncate, this has two variants. The first one is what we call a full shrinking of space, and that is the default. What shrink space does is, unlike moving data around on a block by block level like alter table move, alter table shrink space you can think of as starting at the high watermark, the top end of the table for lack of a better term, and picking off rows in there and trying to insert them into lower parts of the table. Effectively, we're walking backwards through the table to find the highest of the rows with respect to the high watermark and trying to shuffle them into blocks lower in the table. In that way, we will free up space in and around the high watermark, thus letting us move the high watermark downwards. The second variant is alter table shrink space compact, which does the exact same process but does not shift the high watermark at the end of the operation. This might seem a bit of a wasted effort. Why would I want to shuffle all the rows around and still not move the high watermark? This is a hangover from the way we lock the table during this operation. Alter table shrink space can be run predominantly online. While all those rows are being shuffled around in order to reclaim space, the operation can be done without interruption to services. However, at the moment we decide we completed all the row shuffling and need to adjust the high watermark, at that particular moment we need a small lock on the table such that no one else is going to be fiddling with the high watermark while we adjust it. This is why we offer the shrink space compact action. We can move all the rows around without interruption to service and yet defer the moving of the high watermark until, for example, say a quiet time in which we know the impact of locking the table is going to be at its lowest. So hopefully you now have a good understanding of the high watermark concept. It represents the last block used in a table, and that's where a full scan will always have to go up to in order to look for rows in your table. And now, somewhat of a revelation, having explained that we have this single thing called the high watermark in a table, I was a bit loose with the truth. In modern versions of the Oracle database, we have two high watermarks. We have a high watermark and a low high watermark. I chuckle because that sounds ridiculous. A low high watermark? What does that mean? To understand the concept of two high watermarks, we need to look at a little bit of history as to how we used to manage the allocation of blocks to a table as rows were being inserted. Let's go back to my simple example where I said I've inserted 100 rows into my empty table, and those 100 rows as they were being inserted slowly filled up blocks 1, 2, 3, and 4. Obviously, if you've spent money on an Oracle license, you're probably planning on inserting perhaps more than 100 rows in your table, and you're hopefully planning to have perhaps a busy system. You want to be able to handle lots of concurrent inserts because, after all, you went out and spent money on a very sophisticated database engine. If I do have a busy system, which is doing a lot of concurrent inserts, every single one of those sessions is at some point, as it goes to insert a row, effectively asking the database, hey, what block should I put this row into? Because as block number 1 slowly gets filled, I'll need to advance the high watermark, and then I need to tell all those sessions that are clamoring to insert rows they should be using block 2. And then as soon as block 2 is filled, I need to advance the high watermark to block 3, and then tell all the sessions, yep, you now need to use block 3, and so on. To use a metaphor, let's say I had a group of people in a team and they were laying out dominoes to do one of those domino toppling things that always look amazing on those Guinness Book of Records shows. It would be very inefficient for each person in the team to lay one domino and come back to you, and in this case I'm the high watermark, and I would give them another domino and they could go lay that, then they come back. It'd be much better for me to give each person a batch of dominoes and say, okay, go ahead and use them, And when you've used them all up, then come back, I'll give you another batch. And that's what the database does as well. When you do an insert into a table and you need to add one row, rather than advance the high watermark just by one block as we start using that block, we advance the high watermark by a number of blocks. Inside the database, there's a hidden parameter called bump high watermark count, which used to be set, I think, to 10 or 5 in older versions. It's typically 0 now, and I'll explain why that is shortly. But that would be the number of blocks that we would advance the high watermark by in order to not have to continually advance the high watermark by one block at a time. Let's assume it was 10. As a session starts inserting a row, it needs to bump the high watermark up. We would bump it up by 10, which means there are about to be 10 blocks available for that session to use. We'd grab those 10 blocks, we would format them, and as you've seen in my previous episode where we talk about blocks have a structure, we would format them with things like the block header, the block trailing information, the interested transaction list, etc. We would format those blocks. Now we have 10 blocks ready for sessions to use, and then sessions would slowly fill up those 10 blocks. When they do, we would bump the high watermark up by another 10, format those new 10 blocks, and so on. But exploring a little further down that path, if I bump the high watermark up by, say, 10 blocks every time I need to advance the high watermark, that means I effectively have this batch of 10 free but formatted blocks that I now need to manage. As sessions come along, they need to know which block they should use. And of course, it's not just a case of those 10 brand new blocks I've got. I may have some existing blocks in my table that are not yet full, or they may have been full in the past and now someone has deleted sufficient information that they're now ready for more rows to go back in. I need some sort of management in order to effectively hand out those blocks as people want to insert rows into my table. I need some mechanism of tracking which blocks are free for use. By way of naming, I need a list of free blocks. And you may have seen in the DDL for tables, if it gets generated from your SQL developer session or similar, you'll see we have a thing called the free list definition for a table. As the name suggests, a free list was a linked list of which blocks were free for a particular table for which new rows could go into. By definition, all these blocks must be under the high watermark because the high watermark represents the very last block in the table that could possibly be used. All those blocks under the high watermark might already be used, in which case the next insert would then advance the high watermark. But more likely is a select number of those blocks are still capable of holding more rows to be inserted, and the free list would hold that list of blocks. If you're an old school DBA like me, you would be aware that free lists used to be something we used to carefully manage when it came to building our tables. The reason we needed to carefully manage it is if you've got lots and lots of sessions clamoring to insert rows in a high concurrency system, then it wasn't the blocks in the table that became an issue. It was the blocks on the free list. If a lot of sessions are saying, yes, I want to insert some rows, where's the next best block to insert it to? They would be aggressively asking the free list management for which blocks to use. To overcome that, in some version of Oracle, way back probably in Oracle 6 or 7, we had the concept of multiple free lists. Therefore, rather than just a single list of free blocks on a table, we could have multiple sets of blocks on a free list management system that could be allocated to sessions, in that way reducing the contention. Then, of course, parallel server and later RAC, real application clusters, came along, where we've now got multiple machines and multiple instances all wanting to insert data into the same table. Each one of those is going to be asking for access to blocks on the free list, and so we introduced the concept of free list groups. In that way, an individual group of free lists could be allocated to particular Oracle instances running on different machines. Once again, all about spreading out the list of free lists such that we could reduce contention for those free list blocks as we try to insert rows at great speed. You can possibly see where this is heading. We started off with simply advancing the high watermark. Then we introduced the concept of a list of free blocks. And then we had multiple free lists. And then we had free list groups. The complexity just to manage the allocation of blocks in order for someone to insert rows seems to be growing and growing and growing across various Oracle releases. And at some point, I think it was back in about Oracle 8i or 9, Someone inside Oracle said, let's give this a rethink and redo it from scratch to solve these problems once and for all. And we came up with Automatic Segment Space Management, or ASM for short. I've spoken about Automatic Segment Space Management to some degree in my previous episodes on table spaces, but effectively we're running a set of bitmaps in the data files themselves to control which blocks are free within a data file. Those bitmaps allow the database to know for each block in a data file whether it's fully used, fully empty, ready for use, etc. As part of this migration to Automatic Segment Space Management, we also did a little bit of a rethink in terms of the formatting of blocks. As I mentioned earlier, with the old style high watermark advancement where we might bump up the list of free blocks by say 10 at a time, we would say, yep, we need 10 new blocks. We'd grab those 10 blocks, we would format them ready for use, and then give them to sessions to insert blocks into. That is a bit of a wasted effort if a session only needed 2 new blocks, and yet we went to the effort of formatting another 8. Other sessions hopefully will take advantage of that later on, but it's a little blip in performance while we format those blocks, and one session pays that penalty. Under Automatic Segment Space Management, now when a session comes to us and says, yes, I need a block, and we go get a batch of blocks that are free, we don't format all of them. We're a little bit lazy, I like to call it more efficient. We just format some of the blocks and leave the rest unformatted. This gives rise to the concept of 2 high watermarks. The low high watermark is very similar to the historical high watermark we had before. It represents the place in the table where all blocks underneath it are in use and formatted by table, and it contains data. Above this low high watermark might be some blocks that have been allocated to the table, but they're not yet formatted. As I said, we're not formatting all the blocks every time we bump up the high watermark. The high watermark indicates the very last of these blocks. Let me hopefully add some more clarity to that by using a simple example. Let's go back to our original table, which currently has 100 rows in it, and the high watermark is at 4 blocks. Blocks 1, 2, 3, and 4 are in use. I need to insert just a couple more rows, and there's no room in these existing 4 blocks. So I go to the database and say, I need to advance the high watermark, or I need some more blocks, please. The database says, yep, I'll give you a batch of 10 blocks. So I now have in total for this table 14 blocks at my disposal. The original 4 plus 10 the database has just given me. But in those 10 the database has just given me, it may have only formatted, say, 2 of them. What that means is I have my original 4 blocks plus 2 freshly formatted blocks into which data can go into. My low high watermark is hence 6 blocks. 4 blocks plus 2 formatted blocks. But as I said, the database gave me a fresh set of 10 in total. There are 14 blocks in total. So I have 6 blocks that are formatted, and I have 8 left over that are unformatted. My high watermark is hence 14 blocks. Blocks 1 to 6 are formatted, therefore that's my low high watermark, and blocks 1 to 14 all belong to this table, so the high watermark is 14. Why do we need this distinction between the low high watermark, where all the blocks are formatted, and the high watermark, where the blocks are potentially not formatted? The first reason is for performance. If I'm reading a table, I'm going to cycle through every single block. As I read each block, it's useful for me to know if that block is already formatted, because then I know I can immediately jump past the block header, find the row directory. You can see my block internals podcast episode for that one. But I know that if the block is already formatted, it's very efficient for me to jump straight into it, know that the structures are going to be there, and go ahead and read the data. In this case, I know that blocks 1 through 6, the original 4 plus the 2 new ones that are formatted, are formatted for me. All blocks up to the low high watermark are formatted, so I don't need to do any extra work besides just jump into the block and read the rows out. Blocks 7 all the way through to 14, as I mentioned, are possibly unformatted. They might be formatted as well. As I continue inserting rows, remember all the blocks up to the high watermark, all 14 blocks are allocated to this table. I just know that when I originally grabbed that new fresh set of 10 blocks to grow my table, I only formatted a couple of them. The remaining 8 are allocated to my table and might contain rows as I continue inserting. They might be formatted, they might not be. But because I'm not sure, I need to know that I might need to look at each block and see if it's been formatted. Has it been used yet by this table for real data? It's more work to check those blocks. This is why I want to keep a track of the low high watermark, in this case, which was block 6. If I know that everything below the low high watermark is formatted, that makes things efficient. Once I go past the low high watermark, I now have to do a little bit more work because I need to check each block to see if it's formatted. If it is, then it's probably going to contain data. If it's not formatted, I know by definition it can't contain data and I can simply ignore it. But that distinction between a formatted block and an unformatted block is important in terms of saving work. The other reason is for when I'm doing a direct load. If you're doing a insert with the append hint, most people know that that always goes into brand new blocks. It doesn't touch any of the existing blocks in the table. And the reason we do that is by inserting past the high watermark, we always know that that allows us to do an instant rollback. Because if I simply roll back, I simply discard those blocks. I don't have to go and clean up any mess inside the existing formatted blocks. Thus, in order to know where a direct load can commence, what blocks it can start with, I need to know what the high watermark is, because all those blocks between the low high watermark and the high watermark are potentially going to be used by normal conventional DML. I need to start after the high watermark to be absolutely sure that these are blocks that have never been used by this table. So the low high watermark gives me a performance benefit for when I'm doing queries, and the high watermark, besides being the logical physical end of the table, is needed so I know where direct mode operations can start. So let's wrap up this episode. I commenced this episode by saying I was going to talk about all the different types of tables, but that was going to be too much. Then I thought about, let's talk about create table, and that was too much. Then I thought about, well, let's think about DDL, and that was too much. And ultimately, I think we've just burned a good half hour talking about inserting perhaps one row into a table and all the stuff that goes on behind the scenes just to know where that row should go and where subsequent rows should go and how a table would grow as those rows come in. So yes, we've just spent 30 minutes on a thing called the high watermark. We've moved from one high watermark to 2 high watermarks, but hopefully now you have an understanding of the amazing complexity inside the simple act of adding rows to an Oracle table. Thanks for joining me, and I'll see you on the next episode, and we'll continue on with Back to Basics, and hopefully we'll tackle more of the bits and pieces and the intricacies of Oracle tables. Bye for now. Thanks for listening to this podcast. The music credit goes to Zanman from Pixabay Music.